Hi class, welcome to week 2 of our summer online course. I wanted to do a quick lecture for you guys in our final section of chapter 10, and I want to just do a quick video on polar coordinates for you guys. So it's pretty simple to understand polar coordinates and to see how they're used. I will say that your other videos this week are a lot of third-party videos that I didn't do. They're actually, I'll be honest with you, a lot better than I think I would have done. So I encourage you after this quick video to hop over and watch all the other lectures this week. Alright, so what's the deal with polar coordinates? Alright, so a coordinate system, like the one that we're used to seeing, the Cartesian coordinate plane, represents a point in a plane by an ordered pair of numbers called coordinates. Now you're used to seeing this as x and y. Alright, so usually we use Cartesian coordinates where directed distances from the two perpendicular axes, like the x value. Positive x values go to the right, negative x values go to the left, positive y values go up, negative y values go down. Alright, but what we want to now describe is a coordinate system introduced by Newton, and this one is called the polar coordinate system, alright, which later on in different sections can be a more convenient way for many purposes, especially for integrating certain types of problems. Okay, so we choose a point in the plane, and that point is called our pole, or in this case it's our origin, but when we're dealing with polar coordinates it's the pole, and we label it as O. Then we draw a ray, a half a line starting at O, called the polar axis. So we have O, which is like a point here, and then we have a ray that shoots out to the right. That's our polar axis. Alright, so the axis is usually drawn horizontally, like I was just showing on the previous slide, to the right, and corresponding to the positive x-axis in the Cartesian plane. So here is our pole, and then we have our polar axis. Here's our ray, right? So if we have a point P, so out here will be a point in our plane, all right? We'll let R be the distance from O to P, so R to P. If you want to think about this, where this is going, this R is going to be kind of like the radius, all right? So from here to here, that distance is R, all right? And then we let theta, all right, be the angle usually measured in radians between the polar axis and the line OP, as in figure 1. So we have the radius and we have the angle here. All right. These 2 points now, or excuse me, these 2 values here can be used to represent the points. Well, what's our angle, and then what's the radius? And if you guys think back to your pre-calculus, that's how we kind of describe points on the unit circle. All right. In that case, the radius was always 1, but this was kind of how we introduced trigonometry. All right, so then the point P is represented by the ordered pair, not x and y, but r and theta. All right, and these are called the polar coordinates of P. We can use the convention that an angle is positive if measured in the counterclockwise direction. Like, let me go back like this. This is counterclockwise, so theta will be positive. All right. And negative if it's in the clockwise direction. So if you have, let me go back here. If we have a negative theta, that means we go this way, clockwise. All right. If P is equal to 0 and R is equal to 0, then we're going to agree that 0, theta, all right, represents the pole for any value of theta. All right, that's just going to be this right here. All right, so we want to extend the meaning of polar coordinate, r theta, to the case in which r is negative. And so it seems a little weird, all right, but this is how we're going to do it. By agreeing that, as we see in figure 2, the points negative r theta and r theta. So here's r theta, and here's negative r theta. These guys lie on the same line through O, and at the same distance, the absolute, or the magnitude of r from O, but on opposite sides of O. So if I say this is r theta, well, the flip of it on the same line but in a different coordinate, like this is in, coordinate system, or quadrant 1, this will actually be in quadrant 3 over here. Notice how that the theta is the same, but the negative radius has you going in an opposite direction. So the negative value in r goes the opposite way. All right. The cool thing that you know, if you remember from the unit circle repeats itself every 2 pi. Well, this and here, this distance right here is just an additional pi. All right, so this to here is just a half a turn on the unit circle, so it's the same thing as theta plus pi. All right, so if r is greater than 0, so positive radius, the point r theta lies in the same quadrant as theta. If r is less than 0, it lies in the quadrant on the opposite side of the pole. Notice that negative r theta represents the same point as r theta plus pi. So that's another way you could use it or see it. All right, so let's plot these points whose polar coordinates are given. All right, so this is radius 1, angle theta 5 pi over 4, radius 2, angle 3 pi, radius 2, negative angle, I'll explain that, negative radius here, and then angle 3 pi over 4. All right, so you can see through these as I plot them here. All right, here's the first one. So we have our pole and our polar ray here. The angle 5 pi over 4 goes all the way around here. This is radius 1. Angle 3 pi goes a full 2 pi around on the circle, and then another pi, and then out to 2. Negative 2 pi over 3 for the angle, so it goes clockwise, and then radius 2. Now this one is a little weird, all right, here, because remember the negative radius. So we're going to go out to 3 pi over 4, gets me out here. Well, then the line that goes through 3 pi over 4 goes all the way over here, and instead of being up here at 3, we're down here at negative 3 because we're in the opposite direction. All right, so that doesn't seem too bad. Just a different way of showing x and y, just radius and angle. All right, notice that in part D, the last one, the point negative 3 pi over 4 is located 3 units from the pole in the fourth quadrant. That's because the angle 3 pi over 4 is in the second quadrant. All right, and that negative radius, just remember, opposite direction, opposite, different way. All right, in the Cartesian coordinate system, every point has only one representation, but the thing is, in the polar coordinate system, each point has many representations, and actually there's an infinite number of ways you could represent things. So for instance, the point 1, 5 pi over 4 can be represented with a negative angle, negative 3 pi over 4, radius 1. All right. This one over here, 1, negative 3 pi over 4. Oh gosh, that could be 1, 13 pi over 4, or negative 1 pi over 4. They all get you to the same place. So there's multiple ways you can represent a point in the polar coordinate system. All right. In fact, since a complete counterclockwise rotation is given by the angle 2 pi, the point represented by the polar coordinates r theta is also represented by r theta plus 2n pi, and then the same thing as negative pi theta plus 2n plus 1 pi. That 1 pi is because it's theta plus pi. And this is where n is any integer. So there's an infinite number of integers, so there's an infinite number of ways to represent any single point in the Cartesian, or excuse me, in the polar coordinate system. All right, so the connection between polar coordinates and the Cartesian plane can be seen below in Figure 5, in which the pole corresponds to the origin, right here. So the pole is the origin, and the polar axis corresponds to the positive x value. All right, so this is still our radius. Here's our x and our y. You can see this triangle that you guys have seen before in pre-calculus. Now we can draw a circle that has radius r, so it's going to go through this point, and then you can use your SOHCAHTOA to figure out how to convert between r theta and x and y. All right, so if the point P has the Cartesian coordinate x, y, and polar coordinates r theta, well then from that figure, all right, remember like cosine is adjacent over hypotenuse, sine is opposite over hypotenuse, if you remember that from SOHCAHTOA. So cosine of theta is equal to x over r, adjacent over hypotenuse, cosine of this. Sine of theta is opposite over hypotenuse, so sine of this is y over r. Cross multiplying the r over, you have your conversion just like this. So the x value, if you have the if you have the polar, is r cosine of theta, and y is just r sine of theta. All right. So although equation 1 is reduced from Figure 5, which illustrates the case when r is positive and we have an angle less than 90 degrees, these equations actually are valid for any r and any theta. So it doesn't matter if it's greater than 90 degrees or whatever the value of r is. All right, equation 1 allows us to find the Cartesian coordinates of a point when the polar coordinates are known. So to find r and theta, all right, when x and y are known, so this is a little different. This is, you know, x and y now. You can use r squared is equal to x squared plus y squared. That's just the equation of a circle. And then tangent of theta is equal to y over x, right? Because tangent is opposite over adjacent. All right, so these can be deduced from equation 1 or by simply reading the figure, you know, like if you remember your pre-calculus. All right, so let's do a couple examples. So let's convert the point 2 comma pi over 3 from polar to Cartesian coordinates. So these are polar coordinates, and I want to get the x, y corresponding values in the Cartesian coordinate system. All right, well, since the radius is 2 and the theta is pi over 3, this equation 1, if you go back here, right here, the x value is r cosine of theta, and y is equal to r sine of theta. So x is equal to r cosine of theta. Well, this is just 2 cosine of pi over 3, which I believe is 1/2. Yep, so 2 times 1/2. The x value is just 1. So the y value now, y is equal to r sine of theta. Well, that's 2 times sine of pi over 3, which is 2 times the square root of 3 over 2. You can just look that up on your unit circle, which is just the square root of 3. So the point 2 comma pi over 3, all right, is equivalent to 1 comma the square root of 3 in the Cartesian coordinate system. That's it. So very, very, very easy conversion there. All right, so let's represent this point, 1, -1, in terms of polar coordinates. Well, for this, you're going to, let me go back, you're going to need to use equation 2. So I know the x and y, so I can find the r. I know the y and x, I can find the theta. All right, let me get back there. All right, so if we choose r to be positive, all right, in this case, then remember, if we choose r to be positive, we'll have, think about what that means in terms of what the angle will be, remember, okay? So then r is equal to the square root of x squared plus y squared. This is just the square root of 1 squared plus -1 squared, which just gets me the square root of 2. So that's the radius. All right, so now tangent of theta is equal to y over x. Well, y over x is -1. So when is tangent of theta equal to -1? All right, well, that would either be at negative pi over 4 or 7 pi over 4. So one possible answer here, if we have a negative angle, would be the square root of 2 and then negative pi over 4. But the corresponding positive angle would be the same thing as square root of 2 comma 7 pi over 4. And that's it. So that's some real simple algebra to convert between Cartesian and polar coordinates. All right, so just some notes. Equation 2 does not uniquely determine theta when x and y are given. That's because as theta increases through the interval, all right, from 0 to 2 pi, each value of tangent of theta occurs twice, so be mindful of that. Therefore, in converting from Cartesian to polar coordinates, not good enough just to know r and theta that satisfy equation 2. All right, be mindful of that. So as in example 3, we must choose theta so that the point r theta lies in the correct quadrant. So just watch out for that. All right, guys, thanks a lot. Please watch the rest of the other videos. They'll do a good job explaining vectors to you guys. And let me know if you have run into any trouble with your homeworks.